In this program, we'll look at the theory, operation, and testing of the supplemental restraint system installed in 1984 through 1989 model year vehicles. As you can see from the booklet that came with this program, there have been many changes to the system since its introduction. So it's important to be aware of which version of the SRS you're working with. We'll talk about the various versions later on. But for now, let's begin by looking at the theory behind the supplemental restraint system and why it was developed. In a 15-mile-per-hour frontal collision against an immovable barrier, the vehicle comes to a stop about 1/10 of a second after contact. But an unrestrained driver and front passenger continue moving forward at 15 miles per hour, impacting the steering wheel, the dashboard, and the windshield. The potential for serious injury in such a crash can be compared to a fall from a second-story window. In fact, most injuries occur when the occupants contact the vehicle interior in what has been termed the second collision. The most effective restraint system for preventing the second collision is the standard 3-point seatbelt. In full or offset frontal impacts, in rollovers, and in some side impacts, the seatbelt can provide life-saving protection. The proven value of the seatbelt encouraged the engineers to design a system that enhances and supplements its usefulness as an occupant restraint. In order to do this, they first looked at the limitations of the seatbelt. For example, in a frontal collision, the portion of the belt wound around the retractor reel must first be drawn tight around the locked reel before restraint can occur. This, coupled with the stretch inherent in the belt itself, can mean almost 8 inches of additional forward head and shoulder movement toward the steering wheel or dashboard, which obviously means greater risk. To overcome these limitations, the emergency tensioning retractor, or ETR, was developed. Let's take a look at the ETR. It consists of a piston within a cylinder and a gas generator. The piston is connected to the seatbelt retractor reel by a cable. When the chemical propellant is ignited, it forms an expanding gas that drives the piston up the cylinder. Remember that additional head and shoulder movement we just spoke about? Well, the ETR compensates for it by a cable connected to this piston that turns the seatbelt reel and tightens the belt before the occupant moves forward. One reason for developing the airbag is easy to see. The steering wheel and column are only inches from the driver and pose the greatest threat in the event of a frontal collision. The airbag is made of neoprene-coated nylon and is housed in the steering wheel. It inflates fully by means of a gas generator even before the driver contacts it. Instead of meeting with a hard surface, the head and upper body are cushioned by the harmless gas that fills the airbag. The bag then immediately begins a controlled deflation through vent holes in its underside. The gas that fills the bag is produced by the ignition of a solid chemical propellant. An igniter, called a squib, is located here in the center of the propellant housing and is activated by an electrical current. The squib ignites a chemical propellant which produces a gas that travels through these ports. The nylon airbag is then inflated with a cushion of gas that consists primarily of non-toxic nitrogen. The entire process can take place in less than 1/10 of a second. Now, let's turn our attention to another SRS component, the knee bolster. In order to restrain occupants in a frontal impact, only 3 locations on the human body can be used: the chest, the pelvis, and the thighs. For an unbelted driver, the knee bolster limits the movement of the lower body during an accident by restraining knee and thigh movement. The knee bolster is simply a corrugated metal tube, about 4/10 of a millimeter thick. By using a corrugated tube, the engineers obtained the same deformation quality as a smooth metal tube over 3 times as thick, and thus saved weight. In a frontal accident, the knee bolster absorbs the energy transmitted by the driver's knees and thighs and helps reduce potential injuries to the driver's lower body. Okay, now let's take a look at how the supplemental restraint system operates. The brain of the system is the crash sensor. It's bolted here to the transmission tunnel. The sensor does 4 things. It monitors and signals the readiness of the system. detects a major frontal impact, it deploys the airbag and ETR, and finally, the crash sensor stores information about the system in memory. Inside the crash sensor is an accelerometer that measures deceleration. The rate of deceleration and the duration of the signal can trigger the SRS in a head-on or offset frontal collision within approximately a 60-degree arc. Additionally, a mercury switch is incorporated into the sensor to act as an arming or fail-safe device. The mercury switch is engineered to complete the triggering circuit only when the deceleration exceeds a specified limit. These features combine to ensure that the SRS will only trigger during the type of frontal collision it was designed for. For example, it will not activate during quick stops or when running over a pothole. Incidentally, the placement and orientation of the crash sensor are critical. Never rotate or relocate it to make room for accessory items like telephones or aftermarket electronics. Also, for the sensor to work, this arrow must always point toward the front of the car. Okay, let's take a look at the schematic for the crash sensor. The accelerometer senses deceleration acting on the vehicle. The signal generated by the accelerometer passes through a filter, an amplifier, and a limiter before passing through to the threshold evaluation switch. If the deceleration threshold is exceeded, a voltage signal will be sent to deploy the airbag and ETR. But deployment will only occur if the mercury switch connects the power circuit. This circuit will remain disconnected whenever the vehicle is in a normal driving mode. All right, we've just seen that the crash sensor detects major frontal impacts and triggers the SRS. It also stores system information and monitors the readiness of the system. Now let's look at two other components in the system: the energy accumulator and the voltage converter. If as a result of an accident, the battery were to be immediately disconnected or destroyed, the energy accumulator would supply power for 100 milliseconds to the crash sensor and SRS triggering circuits. If the battery voltage drops below normal, the voltage converter will step up the voltage and supply the crash sensor and energy accumulator. Now that we know the theory behind SRS, we can begin to troubleshoot problems in the system. A problem will be indicated by the SRS lamp in the instrument cluster, which is connected to the monitoring circuit in the crash sensor. The light should come on, then go out after a brief delay with the ignition key in position 1 or 2. The light indicates a malfunction if it does not come on at all, it does not go out after about 10 seconds, or if the light flickers on and off while driving. If any of these indications are present, you'll have to troubleshoot the system. On pre-1988 vehicles, you'll use this tester. On 1988 and later models, you'll use the blink code, which we'll talk about shortly. But before we begin troubleshooting, a few words of caution are in order. Like other components in the automobile, SRS has the potential for causing injury if certain precautions aren't observed. To avoid trouble, never remove or install any system components without first switching off the ignition, disconnecting the negative battery cable, and covering the terminal with an insulating sleeve. The red 10-pin connector in the passenger footwell must also be disconnected in order to further isolate the system. Let me list a few more don'ts that you must be aware of. Don't apply any kind of lubricant to the contact rings in the steering wheel. Normal paint drying temperatures are okay, but do not expose the airbag or ETR to temperatures above 212 degrees Fahrenheit. Don't install an airbag or ETR which has been dropped from a height of more than 20 inches. Do not make any electrical checks of the airbag or ETR unless they are installed in the vehicle and you are using the SRS tester. Use of other testers, especially analog meters, can cause the airbag or ETR to deploy. Additionally, if the vehicle has been involved in an accident, there are a few points to keep in mind. Before you use an electric welder, be sure to disconnect the battery, insulate the negative terminal, and disconnect the red 10-pin connector. These same precautions apply if straightening on a body repair bench is needed. If the airbag and ETR have deployed, they must be replaced. If they have not deployed but show physical damage, they still must be replaced because repairs are not possible. Also, normally after a deployment, the horn contacts and slip ring on the steering wheel are damaged and must be replaced. The energy accumulator, crash sensor, voltage converter, and SRS wiring harness may be reused, providing they check okay with the SRS tester. All right, let's start checking the system. But remember, in this section of the program, we are dealing only with 1984 through 1987 systems. This is important because beginning with 1988 model year vehicles, you cannot use this tester. A blink code or an impulse counter is used instead. Now, after disconnecting the battery and insulating the negative terminal, remove the 10-pin connector and plug the tester in. Reconnect the battery in order to run the tests. Let's take a look at the quick test procedures and see how they are used to locate the possible problem area. First, we check the SRS voltage supply by turning the tester to position 1. With the ignition on, the LED must light and the meter must show battery voltage. If it does not, low battery voltage or a problem in the wiring harness can be suspected. Turning the tester to position 2, the LED must light, and we need a reading between 11 and 13 volts continuously for about 30 seconds. If this is not obtained, the voltage converter, energy accumulator, or wiring harness can be suspected. Test step 3 checks the resistance of the wiring, airbag unit, and slip rings. We'll turn the steering wheel to the left and right stop so that the brushes move over different points on the slip rings. As you can see from the chart, we should maintain a reading between 2 and 10 ohms. If not, we can suspect a poor contact between the slip ring and carbon brushes, defective wiring, or a defective airbag unit. Under no circumstances should any kind of lubricant be applied to the slip rings. Even a small amount will definitely cause problems. The second part of test 3 checks for a short to ground in the wiring. With the ignition on, push this button on the tester. The LED must light, and we need a reading from 20,000 ohms to infinity. If not, the wiring harness or airbag should be checked. By the way, infinity is indicated on the tester by the letter E repeated 3 times as here. By switching the tester to position 4, we can check the resistance of the ETR circuit. Incidentally, the resistance value will differ between a vehicle equipped with just a passenger side ETR and a vehicle with a passenger and driver's ETR, such as we have here. With the ignition on, the LED must light, and we need a reading of between 2 and 5 ohms if only a passenger side ETR is installed. If the car is equipped with both the driver's and front passenger's ETR, the correct reading will be between 1 and 1.7 ohms. While still in position 4, check the circuit for a short to ground. Press the button on the tester. The correct reading is from 20,000 ohms to infinity. Test 6 checks the energy accumulator. Both the LED and the capacitor symbol must illuminate. A reading of 9 or greater means the wiring to the energy accumulator is okay. Position 7, the last step in the quick test, is to check the capacity of the energy accumulator. With the ignition on, this LED must light. When the light goes out, read the meter. The correct reading will be either 4 or 7 microfarads, depending on the energy accumulator installed. That information is given in the retention book. The tester can also be used as a volt-ohm meter when performing the detailed SRS tests. Okay, that completes the quick test program. Let's summarize some of the key points we've made. To review, the supplemental restraint system, as used in model years 1984 through 1987, consists of an emergency tensioning retractor, a driver's side airbag and knee bolster, a crash sensor, an energy accumulator, a voltage converter, and the SRS light. When a severe frontal impact occurs within approximately a 60-degree arc, the system will activate in order to supplement the protection provided by the three-point seatbelt. The crash sensor's accelerometer measures the deceleration force and duration. The separate mercury switch inside the sensor will arm the triggering circuit only when a sufficient deceleration has been reached. The voltage converter maintains a minimum of 12 volts to the SRS if the battery voltage drops below normal. The energy accumulator will maintain power to the SRS during an accident if the battery is disconnected by the force of the accident. The SRS light in the instrument cluster indicates certain electrical problems in the system. It should light with the key on and go out after approximately 10 seconds. Now, beginning with model year 1988, the supplemental restraint system incorporated a control unit with energy accumulator, voltage converter, and crash sensor integrated in one housing. This single unit eliminated the separate components and is mounted in the same location as the earlier crash sensor. As previously mentioned, a problem is present in the system if the SRS warning lamp does not light, or if the warning lamp stays lit. But beginning with model year 1988, the cause can be diagnosed by a blink impulse readout provided by the SRS warning lamp. In fact, because of the 1988 model year changes to the system, the test adapter previously used for diagnosing SRS cannot be used for testing 1988 and later model year vehicles. To obtain diagnostic information using the SRS warning lamp, terminal 1 and 6 of the test connection are connected to a jumper cable. To initiate the diagnostic test, the ignition must be on and the jumper button pressed for 2 to 4 seconds. This will cause the SRS lamp to blink out a diagnostic code. If the lamp blinks once, there are no faults in the system. If the lamp blinks more than once, observe how many times and record the number of blinks. Then, check to see if another fault is present by again pressing the jumper button for 2 to 4 seconds. If no other faults are present, you will see the same number of blinks again. If there is a second fault, the blinks will continue to count and stop at a higher number. Repeat that procedure until all faults are recorded. The test procedure is facilitated with the use of the impulse counter, which eliminates the need for counting blinks. The counter leads are connected to the test plug. When the power input is connected, the LED will illuminate to indicate that the voltage supply is correct and that the tester is functioning. With the ignition switched on, press the start button for no less than 2 and no more than 4 seconds. A number from 1 to 10 will appear. The number 1 indicates that there are no faults stored in the system's memory. Numbers 2 through 10 relate to a particular fault in a component or circuit. Determine all fault codes by repeatedly depressing the start button for 2 to 4 seconds until the first fault code number is displayed again. Performing further detailed testing may require the use of the socket box tester and an appropriate multimeter. The SRS has a hard memory feature, meaning that disconnecting the power supply will not erase fault codes stored in the memory. So, after a problem has been fixed, the code must be erased by using either a jumper button or impulse counter. First, you must recall the fault code. After the fault code is displayed, wait 3 seconds to allow the system to ready itself, then push the impulse counter or jumper button for 7 seconds. If you should mistakenly exceed 8 seconds, a false code 9 may be programmed into the system. It must then be erased also. Each fault code in the memory must be erased one at a time in the same way. An exception is fault code 10, which is the code indicating an SRS deployment. Code 10 cannot be erased from memory. Therefore, the control unit must be replaced after each SRS deployment. With the 1989 model year, a front passenger airbag was standard equipment on the Model 126 with V8 engine and optional on all models with the 6-cylinder engine, with the exception of the 201 series. Let's take a look at the passenger airbag. But remember, always disconnect the battery first and then the red 10-pin connector. On model 126, use a plastic wedge to remove the trim piece. One 10mm hex head bolt holds the airbag assembly in place. Remove the two electrical connectors for the igniters. As you can see, the passenger side airbag has two gas generators. In order to control the pressure buildup in the interior of the vehicle, they ignite in sequence 15 milliseconds apart. As you know from the previous system, the deployment logic is based on whether the seat belts are buckled and the speed of deceleration caused by the impact. A chart in the retention book for this program summarizes this for you. Let's take a look at a few of the SRS electrical connections found on a 1989 model year vehicle. If you're referring to the wiring diagram, two are right here in the forward center console area by the SRS control unit. The first one is the main power supply connection for the SRS, connector X28-2. That's this round single pin connector. The next one is connector X28-7, which connects the power supply signal to the diagnostic plug. That's this flat 2-pin plug, having only one pin in use. And very important, ground terminals W12, which are among this cluster of several ground wires right here. Now, looking under the seat, you'll find the red connector for the seatbelt buckle switch, similar to the one used on 1988 models. The resistor for the front passenger airbag is located to the left of the right front seat anchor under the carpet on early production 126 models and was later incorporated into the wiring harness. The onboard diagnostic feature introduced in 1988 models was retained for 1989. The 89 system has the same capabilities, but because of the addition of the passenger airbag, the test program was expanded. So be sure you refer to the proper test procedure when performing the test on an 89 model. Let's take a brief look at how you would use the troubleshooting chart to diagnose a problem in this 1989 190D. Since the SRS light has indicated a problem in the system, I've connected the impulse counter. Fault code 3 and fault code 5 are present. Turning to the troubleshooting chart for 1989 model year vehicles, we look under impulse display 3 first. As you can see, impulse display 3 indicates a problem with the driver's side airbag slip ring. By the way, this symbol is for the socket box tester, and this is the symbol for an ohm meter. According to the chart, we connect a DMM5 or fluke ohm meter between terminal 3 and terminal 5 on the socket box. After turning the ignition off, disconnecting the battery, and covering the terminal, the socket box is connected at the X29-9 connector, which is the red 10-pin plug for the SRS. The designations and locations of the connectors are shown in both the retention book and the ETM. Turning the steering wheel completely to the left and to the right checks the resistance of the brushes over various points on the slip rings. If you don't get a reading of between 2 to 5 ohms, you've got a problem with the airbag itself, the brushes, the slip ring, or the wiring. Having found and corrected the problem, the next thing I want to check out is the second fault code I got, which was fault code 5. As you can see from the chart, this checks the driver's seatbelt buckle switch. Notice here that there is no symbol for the socket box, like we had for code number 3. This test simply calls for checking the resistance between pin 1 and pin 2 of the S68 3X connector. Turning to the retention book, you can see that the S68 3X is the connector for the driver's seatbelt buckle switch and is located under the seat. Going back to the chart, I should get 400 ohms, plus or minus 10, with the belt not fastened, and 100 ohms with the belt fastened. If not, I've probably got a problem in the seatbelt buckle switch. You can troubleshoot the other fault codes in much the same way. Just be aware of which ones use the socket box, which is indicated by this symbol, and which don't. And check the retention book or ETM to find the location and designation of the particular connector. Before we conclude, let's look briefly at how the airbag and ETR should be handled. If an airbag or ETR is to be shipped, such as for a warranty return, it must always be put in its original shipping box. Do not deploy the airbag or ETR before returning them. They must be sent in their original condition. The airbag has a useful life of 10 years. It must be replaced by the date shown on the SRS label on the driver's door B pillar. Incidentally, unlike the airbag, the ETR does not have a fixed useful life. Okay, let me show you what to do if it's necessary to dispose of an airbag that does not have to be returned on a warranty basis, such as, for example, a total loss accident vehicle that's being scrapped. Because of the force involved, as well as the odor, dust, and heat that will be generated, the airbag must only be deployed either in an engine cage or a wrecked car. If in a car, it should be securely mounted in its normal installed condition and not lying loose. You'll need this special tool. Connect one end of the cable to the airbag. And if you're using an engine cage, place it on a non-combustible surface with the metal side down, the padded side facing up. When the area is clear, turn the switch to position 1 and press the contact buttons simultaneously. Following ignition, this green indicator will light. One caution: because the gas generator in the airbag becomes very hot after deployment, be sure to let it cool off before handling. Before wrapping up, let's take a moment to review SRS application on the various Mercedes-Benz models. SRS was first installed in the 1984 126 models. It initially consisted of a driver's side airbag and driver's side knee bolster and an emergency tensioning retractor for the right front passenger only. For the 1985 model year, the system was modified and ETRs were installed on all models for both the front passenger and driver. One exception was the 300 CD Turbo, which was not equipped with ETRs. The driver's side airbag and knee bolster were standard on the 500 SEL, 500 SEC, and optional on the 190E, 190D, 380 SL, 380 SE, and 300 SD Turbo Diesel. Beginning with the 1986 model year and continuing through 1987, emergency tensioning retractors on both front seats and a driver's airbag and knee bolster were standard equipment on all models. The 1988 model year saw the introduction of new system components and a self-diagnostic feature. The control unit now combined a crash sensor, energy accumulator, and voltage converter in a single unit. A new deployment logic, seatbelt buckles, and wiring harness were also used. The 1989 model year added a front passenger airbag and knee bolster available on the 124 and 126 models. That concludes our look at the theory, operation, diagnosis, and application of the 1984 through 1989 Supplemental Restraint System. If you have any questions or comments, whether on this or any other Education for Excellence program, please return the postage paid card enclosed with this program.